Okay, welcome back, Science 30s, to our next lesson in chemistry. This is 1.5, and today we're going to be looking at pH. All right, so let's bring up 2 beakers of water, and let's review what was happening with water, acids, and bases. So I have 2 beakers here, and they're filled with water, which is formula H2O, and that's the majority of the molecules, but we said in the last lesson that some of these are going to break up into H3O+, which is hydronium, and OH-, which is hydroxide. And then we talked about how an acid and a base are going to interact with the water. So on this side, let's start with an acid. We said that an acid is going to be a proton donor, so it's got those H pluses, and it's going to give it to the water. We can see the proton going to water, or H2O, that would turn it into hydroxide. And a proton could also be given to OH, which is going to turn that into water. Next, if we look at a base was the opposite. A base was a proton acceptor. So it's going to take protons from this solution. So it would separate a hydronium ion from its proton, so break it into H2O and its proton, and take that proton, because it's a proton acceptor. And then from water, it could take a proton as well and turn that into hydroxide, taking one there. So we had proton donor, proton acceptor doing these things. And we can see in the solutions now on each side that this has a higher concentration or a higher amount of H3O+ hydronium, and this has less H3O+, less hydronium. So to measure how acidic or basic something is, we're going to measure how that hydronium concentration is affected, and we're going to measure it with something called pH. pH kind of relates to power of hydrogen. It's not sure if that's exactly what it was meant, but we can call it power of hydrogen for this video because it's relating to that hydrogen ion, which is the proton, and it has to do if there's been some donated or some taken away. Now the system of pH is going to be describing how acidic or basic, and it's using the hydronium concentration. As we saw, it goes up for an acid and goes down for a base. Now the way that we're going to measure it is with an inverse log, and that may be a bit unfamiliar from math, so we're going to talk about what logarithms are. Okay, so again, log, but this is short for logarithm, is the inverse function of an exponent. So something squared or something cubed is an exponent. This is kind of like the opposite of that. So it's commonly base 10, and that's the only logarithms we're going to look at for this lesson, and because that's used for pH, and it's really one of the most common logarithms. And what it means is this. I think this is a good example. So it says if you have log 10 1,000 equals something you're trying to solve for. So you're trying to solve log 10 1,000, what's that equal? What it's really asking is saying 10 to the what equals 1,000. So the base 10 to the what is equal to 1,000. And our answer in this case would be 3, because 10 to the 3 is 1,000. So 10 to the exponent 3 is 1,000. To go in the reverse direction of that was doing the log. So if I say, what's the log base 10 of 1,000? The answer is 3. So when we use logs for a scale, we're going up by factors of 10, because we're talking about base 10 here. So if we were going to relate this to something else, measuring how loud a sound is coming out of a speaker, I'm going to set up this chart. It's not 100% accurate to how we measure sound, but it'll be an example for how a base 10 or log 10 system would work. So I'm going to look at loudness compared to the volume setting, and I'm going to make a chart here. So let's say that the loudness, I'm just using that as a general term for how loud it sounds, is a 10. That's how loud it sounds to my ears. And maybe that's on a volume setting of 1. Now what happens with a log system or a base 10 system here is that if I increase the loudness, it sounds at 100 now, 10 times louder to my ears. Instead of calling this volume setting 10, we're calling this volume setting 2. Okay, so we went up 1 volume setting and the loudness went up 10 times. Okay. Similarly, if we went up to 1,000, so that's 1,000 for loudness, then the volume setting would be 3. So every setting is going up by a factor of 10. And we can also kind of think of this as exponents, that 10 would be 10 to the 1, 100 would be 10 to the 2, and 1,000 would be 10 to the 3. So that's also what we're going to be looking at for pH. When we are looking at the change in hydronium concentration, to change one pH will be to change by a factor of 10. Let's take a look at how it applies to that. Okay, so a reminder that the pH is the negative log of hydronium ion concentration. So that's the formula there. pH is equal to the negative log of your concentration of hydronium ions. And that's going to be measured in moles per liter. So I'm going to pull up some beakers here and let me try and visualize this. So I'm going to start with the middle beaker, and I haven't put the water molecules, the H2O here. Reminder, that's the majority of them, but some have split into H3O plus and OH minus. So I've put 10 on each side here. Now let's say that I measure the concentration of hydronium ions here, and I get a number of 0.0000001 moles per liter, a small amount. Remember, there's much more H2Os, but there is a small amount of hydronium and hydroxide. Okay, so I measure it to be that. I could also write this as 1 times 10 to the negative 7 moles per liter. I'm going to use that concentration of the hydronium, the red ones there, and plug that into my formula as negative log 1 times 10 to the negative 7. And what I get for my answer is 7. The pH is 7, and this is considered neutral because we have the same amount of the hydronium as we have for the hydroxide. And this is just regular water. We're going to have a really small amount, times 10 to the negative 7, break up into hydronium and hydroxide. And that gets the pH level of 7, which is neutral. Now, what if I start adding an acid or a base? Well, if I start adding an acid, I'm going to increase the amount of hydronium. So I'm going to have that original 10, but now I'm going to have more, added 10 more. Now I have 20, 30, 40, 50, 60, 70, 80, 90, and 100. Okay, I've gone up by a factor of 10 on purpose, so I've increased my hydronium ion concentration by 10. I've gone from 10 to 100. Okay, so we see there's a lot more hydroniums here, but as we saw with the relation to sound, if I've gone up by a factor of 10, that should only change my pH by 1. Let's take a look. So now have my concentration here as 0.000001, so still really small, but it's 10 times bigger than the first one that we had. That can also be written as 1 times 10 to the negative 6. Now I plug that into my calculation, negative log 1 times 10 to the 6, and I get a pH of 6. Okay, so because the negative exponent went down, when I got more hydroniums, my pH number went down. You might think that a lower number means that it's less acidic, but we can see that a lower negative exponent means that's actually a higher amount of hydronium ions. And before I go to looking at if we went to towards the other direction, I noticed that I put a 1OH here. And the reason for that is because we saw before that when we add an acid, it's going to be turning the waters into hydroniums and hydroxides into waters. Those are the two things that are changing. So in this, what we started from were a balance, now we have much more hydronium and only a couple, very small amount of hydroxide. We actually have 10 times more hydronium, 10 times less hydroxide. We'll come back to that in a minute after this slide. Right now, let's go over to the last beaker there, where we're going to look at if we reduced the amount of hydronium. So now we're going to put just one of them. So from our neutral beaker at the start, we've gone down to just 1 or 10 times less, okay? And to do that, you'd have to add a lot of base that is going to be taking away. So we're going to see we're going to have a whole bunch of hydroxides here. Just like we saw in this case with the hydroniums, we're going to have 10 times more hydroxides and 10 times less hydronium. So just the opposite of that. If we're looking at now how much of the red hydroniums we have here, we have 10 times less. So it says 0. Whole bunch of zeros here. 1, 2, 3, 4, 5, 6, 7. Then 1 moles per liter, which would also be easier, more easily written as 1 times 10 to the negative 8 moles per liter. Throw that in our calculation, and we get a pH of 8. So hopefully that shows you that as we go more hydronium, we have lower pH, and less hydronium, we have a higher pH. And that this isn't a factor of just like 2 times or 3 times, but it's a factor of 10 times. You have 10 times less hydroniums you're going to go up a pH. 10 times more hydroniums, you go down a pH. Okay, now that's the calculation that I want you to focus on, calculating pH. But there is another way to represent acids and bases, and it's with pOH. We have changed the top pOH. That's looking at the concentration of the hydroxide. As we saw in the diagram, it's just kind of flipped. When I went down for red hydronium, I went up for blue hydroxide. When I went up for red hydronium, I went down for blue hydroxide. So this is just going to be a flipped calculation. So you can see that in the middle, it's still the same. I have an equal amount of blues and reds. That was just neutral. I had 1 times 10 to the negative 7 reds. I have 1 times 10 to the negative 7 blues. So I still get actually a calculation of a pOH of 7. Okay, now if I'm going to go to this side, okay, I'm going to have less blue hydroxide now, times 10 to the negative 8, because I've gone down by a factor of 10. I went from 10 to 1. Okay, so then that would be the same calculation here. I plug in for pOH and I get a pOH of 8. Now if I'm going to go to this side where I have more hydroxides, where I have 10 times my starting amount, I have times 10 to the negative 6, and I get a pOH of 6. Forgot to put that original pH in there. That was 8 from before. I know I went through that rather quickly, and the reason is I don't think it's really used doing this calculation because there's a much faster way to get to pOH, all right? Because we're mostly gonna be calculating pH. How could you figure out the pOH? What you notice that when we add all of these up, 7 plus 7 is equal to 14. Over here, 6 and 8 is equal to 14, and over there, 6 and 8 is also equal to 14. So this course is mostly gonna ask about pH, and that's the whole calculations we did on the previous slide. And then to find pOH, you just take 14 minus the pH, gives you the pOH. And I think that's probably the easiest way to solve for those. Speaking of solving questions, let's now just do a couple examples before we conclude the video. A solution has 4.5 times 10 to the 4 hydronium ions, or a concentration of 4.5 times 10 to the negative 4 moles per liter. Probably should have put that there. What is the pH? So now we have our formula like we saw on the last slide. pH is the negative log of the hydronium ion concentration. So I just plug in that number there, and I should get my answer. Let's take a look at how we put that in the calculator. Bring the calculator up here. I'm gonna start by putting in the negative. Make sure you don't put minus, actually put the negative, so it's that button there. And then log would be right there. It's gonna give you some brackets. Next, I'm gonna put 4.5. And then for the exponent, you might remember this from the start of the course, is that we're gonna use that E symbol, and that's by pressing second and then comma, and that's gonna bring up that E, and it means times 10 to the exponent. So all I had to put it was 4.5 E, which means times 10 to the, and then I'm gonna again put that negative button, and then 4, get that calculator out of the way, and we can see our answer as a pH of 3.3. Okay, now what if you had a question that went the opposite direction, said you wanted to go from pH to hydronium concentration? I think it's actually even a bit easier to put in your calculator. It's just 10 to the negative pH. So we'll do an example. It says a solution has a pH of 9.2. What's the hydronium concentration? So we'll set up our formula. Again, 10 to the negative pH. So 10 to the negative 9.2. And in our calculator, we're going to put 10. So 1, 0. And then we're going to press this little button at the top there, that little arrow that's going to give us the exponent. And again, we press negative, not minus, we press negative, and then 9.2. And then we should get our answer of 6.309 times 10 to the negative 10. Okay, that seems to make sense because it's a really low concentration, and this is a base because we have a 9.2 pH. This was less than 7, this was more than 7, which was neutral. All right, so a higher pH than 7, which is neutral, is a base. So we have our answer there of 6.3 times 10 to the negative 10. And just before we finish here, I want to add in, if you were asked for the pOH, remember, all we have to do is take the difference between the pH and 14. So we have the pH of 9.2. What's the pOH? We'll just go 14 minus 9.2, and we get our answer of 4.8. Okay, I hope that video helped you to understand what pH is and how it measures acids and bases. Thank you so much for watching this video, and I will see you in the next lesson.